Is it recording?
Yeah.
All right, we're going to get started. Hello, everybody. This is going to be the fourth lecture on ORMs. So to start off, we're just going to go through some logistics. PA3 was due yesterday, and the grade should be out this Friday. I hope you guys have turned it in. And PA4 is going to be released tonight, and it will be due next Sunday at midnight, as always. Just to let you guys know, the last day to drop this course, because it is one of the shorter courses, it's going to be November 20th instead of, I think the normal one is like October 24th. But yeah, last day to drop this course is November 20th. So if you have any concerns about like your standing in this class, of course we want you guys all to pass. So just like feel free to shoot us an email or just like stop by during office hours. All right, so let's get started. So far, we've talked about doing our database interactions with SQL through Python. So just a quick overview of what we've been doing so far. Again, we, the client, are sending requests to the server, and we interact with the database through SQL queries that we execute. And then we get the data back, which we send as a response to the client. And so today we're going to be focusing on this interaction between the server and the database. We've been instantiating connections, and then we've been making like straight up SQL queries kind of inline in our Python code to retrieve or update or post any data. And this has been working out pretty okay. I think generally all of the routes we've been implementing have been fairly straightforward in terms of what our SQL query looks like. But let's try to think about why we might not want to just use SQL when we interact with our database. So there are a couple of issues with using raw SQL. First of, the code is less readable. It's almost English. I mean, select star, select all from table, but once your query starts to get a little more complex and you have to kind of start nesting SQL queries, then at that point it's a little bit hard to parse through what the SQL query is trying to do, especially if you have a ton of queries for each one of your repo routes. It's also susceptible to vulnerabilities, which we will talk about later. And last but not least, you guys might have realized that there's sometimes runtime exceptions if you have something like error found near transactions table or something, and you're like, I have no idea what that means. Like, where am I getting the error? If your query is really long, then you might not know where in that query is going wrong. And it's a little bit harder to catch them because you already have to worry about catching Python errors. And then now when your like SQL query that's run through Python also throws an error, then that's just like another layer of things you have to worry about. So first off, just an example of kind of how complex querying with SQL can be. This is literally one of my responses in the databases course. And yes, this is like a question they asked us to write the SQL query for. It's kind of dumb, it's really long, and I don't even remember what this is for. Like, what is that? So we don't want to, if you have someone else looking at your code base, you want them to be able to easily understand what you're trying to do. And this doesn't really accomplish that. Arguably, the worst thing about using raw SQL is something called SQL injection. So this is one of the vulnerabilities you can have with using SQL. And basically what it is that people outside of like the people using your database might be able to craft an input to trick SQL with their like syntax and semantics into doing something that the maintainer of the database didn't intend for to happen. So this allows database access to, potentially malicious external sources that will either query unauthorized data, maybe like your usernames and your street number or whatever, or they might corrupt or delete existing data. So let's just go through a quick example of what can happen. So this is the breaking login. So of course, I'm sure you've had to log into accounts where you are asked to put in your email and your password. And if you don't have an account or you don't have the password, then you shouldn't be able to get in. But otherwise, you should. How can this go wrong? So imagine if in the backend, when the client puts in their email and their password indicated by the $signs, we have this SQL query. So it's select all from the users table, where the email is the email you inputted, and the password is a hashed version of the password you put in. And MD5 is a way to change like your inputted password. I had to renew my passport, so I've been thinking about that all day. Into something that's not just like your plain text password in the database in case it, gets hacked or something, and then like someone has access to not your actual password. But so say that you as HackerMan supply values as shown here. You have some random email like xx@xx.xx. But then for your password, you put something instead of like what you might normally put for a password. You would have XX, and then you have a closing quote, and then a closing bracket, and then or 1 equals 1. So what the SQL command is going to do is that it's just going to go ahead and put that in for the placeholder values. So we have the email equals XX at whatever. But then you see that the password equals kind of like a different SQL command than the one that was intended. You would have password equals a hashed version of XX, but then after that you would have or 1 equals 1, and SQL thinks that part is just part of the SQL command instead of like your actual password value. And what that might do is shown here. You would have that email evaluates to false, which is because it doesn't exist, and your password evaluates to something false because it doesn't exist. But now you have this trailing condition, or 1 equals 1. And as you know, 1 equals 1 in this logical world, and that evaluates to true. And then as a side note, the thing at the end where it's like the dash dash, that's how you do a comment in SQL. So that will cause like everything after that to not execute. So the SQL command will only be executed up until that dash dash point. So now we have something that looks like select all from users where false and false or true. So false and false is going to evaluate to false, but true will always evaluate to true. So false or true, if you guys have taken like logic, will always evaluate to true. So now you have something that selects everything from users always. And that's not what we wanted, and that's not what the query intended. Now the person who put in that SQL injection will be able to have access to like the accounts or just be able to go into the system, which is bad. Here's a comic, if you know XKCD, that kind of shows what you can do with SQL injection. It's just like some mom named their kid Robert drop table student, and if they put that into the database system and try to do a query with that, then they end whatever query they were trying to do earlier with the semicolon, but then after that it runs another query, drop table students, and now they've lost all of their students table. And the administrator is sad. Be careful. So how can we make our lives easier? We can use something called object relational mapping so that a lot of the problems that we listed before with readability and vulnerabilities can be prevented against. So we usually just call these ORMs, a little easier to say. And what they allow us to do is that we can use objects as abstractions of our database schemas. So because we usually think in an object-oriented manner when we do our programming, hopefully if we've taken like 2110, this is a way for us to query and manipulate data from a database using objects to model the data. And you might have thought that like databases have a very strong kind of connection to what like a class or model might look like, just because in this class we've been using relational databases to model our data. So in effect, we will be able to use somewhat like a database of objects that can be used within the language of your backend. So we can use Python instead of having to switch between like Python and SQL. Yes, it will be very nice. And it allows us to reason about our entries as kind of like instances of an object. And I'll show you how we can think about that. So say we have this very simple table. We have, it's going to be like people. We have ID, first name, last name. This can be represented as a Python object where we have like a class person. And each row is an instance of this class. It can be an object with its own ID, first name, and last name. And it's nice because if you know every row will have the same schema as every other row in a table, and every instance of a class, each object should have the same like fields as the class itself. So the ORM we're going to be using is called SQL Alchemy. There's a couple of them that we can use for Python. I think another very popular one is Django, but we're going to be using SQL Alchemy because it kind of gives a very good balance between abstraction and having control over sort of what you're querying for. It's not good to have something that's too abstract because then you might not really know what you're doing or trying to accomplish, but you also don't want something that's too complex because at that point you might as well just use SQL. But yeah, it's very nice for writing just like more complex database queries. And it's good because it integrates well with Flask, which is what we're using for our kind of like web development servers. There's a framework called Flask SQL Alchemy, as you can guess, that we can use kind of right out of the box for connecting with SQLite, which is what we're using. So let's talk about why or how we might use an ORM, and this will be a case study of one of AppDev's apps, Eatery. For those of you who don't know, Eatery is an app where you can check like locations and menus of both eateries on campus, like dining halls, or in College Town as well. So what data might we want to model in an eatery? So there's a lot of things that the app actually implements, but I'll talk about a few of them. You can imagine you want to know the name of the eatery. You might want to know a little bit of information about it. And in the app, there's like an image that's displayed kind of as like a banner. And let's say you want to know also accepted payment methods, whether it's like BRBs or cash or credit card or a Cornell card, just whether or not you can use BRBs at this place. And there's a lot of other fields that we can also implement. So we can represent each eatery entry as some sort of like eatery object with all these fields that we just listed that can hold these data items. And each non-basic type, say like a payment method, because you know the eateries won't just represent like just one payment method, you are probably able to use multiple payment methods. And so these types can be represented as its own object. So how might we do this in just normal SQL? I think this is pretty straightforward. We create a table, we would have our fields, and then as for our payment methods, we can have another table called payment methods type, and then we can have a foreign key here that will reference one of these objects or one of these rows in the payment methods type. But it's a little hard to look at, especially if you're kind of giving a cursory glance. Right now, it's not too bad to look at because we only have like 5 columns, but in reality, Eatery has like a lot of things that they keep track of, so the model itself is actually quite large. Let's think of a different way that we can model this using what Eatery uses is Graphene right now, which is like ORM used with GraphQL, which is like a querying language. So this isn't going to be SQL Alchemy, but it's very similar. This is what it looks like in Python with Graphene. So we have an eatery here, and we have all of our fields, as we said before, with like an integer ID. And you can see that from before, we have like, say, name is not null, and here we have required is true. We have our image URL and our about, and now we can take a look at, we have our payment methods, which is a field that refers to the payment methods type class, which is listed right below. And so this is like a really, really easy way to reference using like a foreign key, another class. And we have here that we just have like booleans for whether or not we're allowed to use this payment method at this eatery location. So we can talk about the pros and cons of using these ORMs. There are a lot more pros than cons, but some of the pros include having readable code that resembles our query reasoning. So when you take a look at the methods you're calling, you can do like get one and then like parentheses whatever, and then where blah. And it's kind of similar to SQL, but if you're doing more complex queries, then it will look a lot nicer. Then we'll also have abstract SQL-free data representation, so we don't have to boondoggle with SQL again. It's really nice because especially when you start using kind of like multiple databases, we're able to not worry about the specifics of the database implementation, and instead kind of, since we're abstracted away from that, we can be able to switch, or we're just like flexible with how we connect to different databases. We can also have that the database and application logic use the same language. So this is all using Python, no more SQL. And we will have, like I mentioned earlier, strong cross-compatibility with many databases. And finally, there's a lot of like in-place security measures against SQL injection, since you're not directly putting a string into a SQL query. Some of the cons is that, so one of them is that we might have slower query performances for very specific queries. There's a lot of ways to optimize how you can run a SQL query if you have control over the SQL query. And generally, SQL Alchemy will try to make its best judgment on how to formulate from what methods you run, which SQL query to create, but that might end up being like a little slower than what maybe you as a SQL expert might write. Generally, this isn't a big problem, like it's kind of negligible, unless if you're doing something kind of crazy, which I imagine you guys won't be yet. And using these ORMs kind of abstracts away the fundamentals of SQL. So if you start off using an ORM, you might not get that more fundamental understanding of why we use SQL and how SQL works, but because we've already taught you SQL, you don't have to worry about that. And finally, one con is that it might increase application code, because not only would you have to write all like your getter and setter methods, you also have to have like your class code, so like writing out the class abstraction code. But this isn't really a problem. More code doesn't necessarily mean that it's less readable. In fact, I would argue that it's more readable. It's just easier for people to parse through than having that crazy long SQL query. So unless if you're really, really worried about the size of your code, this shouldn't be an issue at all. So that was just kind of a brief overview of ORMs. Connor is going to be giving a demo on how we're going to be integrating SQL Alchemy into our code bases.
Okay, so we are going to begin the demo where we left off last demo, which is in db.py of when we're going through how to use SQLite for the first time. So the first thing, I left this code in here initially just to show off at the end how much less code we'll have and how cleaner it will be. So the first thing we want to do is just get rid of all this stuff, and let's change our imports so that we're using SQL Alchemy. So the first thing we want to do is instantiate our database object. This is just an instance of the SQL Alchemy class, and this will give us many handy methods that will make it super easy to define our models like in a class structure. So the first thing we're going to want to do is create like a table for our task model. So we're going to do that by doing class task, and we're going to subclass db.model. The first thing we want to do is indicate what table, how we want to name the table. So this is indicated by the table name field, and we're just going to call it task for right now. So the reason we choose to set table names is just to make it a lot cleaner and tell SQL Alchemy that like we're deliberately setting things so when error messages come up or things are happening that we don't know what's going on, we at least know the names of everything in there. If we don't provide this, SQL Alchemy and other ORMs typically just auto-generate a table name. They may guess, or they may just have like another algorithm for determining the name, but by deliberately setting it, we have a better shot of understanding what's going on in our code. So we define columns by just doing a simple db.column, and the first thing we want to define is our task ID. So actually, let's call this, one second. All right, so I'm going to define a column, and we are going to first indicate the type. So we're going to do that with an integer. Oh, that's not good. And the next thing we want to indicate is that it's a primary key. So as we learned earlier, primary key enforces that it's unique and also that it will auto-increment for us, which is what we want in our database table. The next thing we want to go for is a description field. So we can define a new column. We can do db.string, and we want this to not be nullable. So we want every task in our table to be required. So we can do our third item, which is done. So we're going to define another column, and we can do db.boolean. And this one too, we want it to be non-nullable. Wait. It's like, yeah. Cool. So the next thing we want to do in defining a class, just like in Python, we want to define how we want to initialize. So we could, just because we have description and done, define these fields like so, but normally, but we're going to use a spread operator and do this common dev trick called spread quargs. So you can imagine quargs as just being like a regular Python dictionary. So in the case of us right now, we could have, say, like description, and then like some field, and then done also be some field. But quargs allows us to just like turn this into a dictionary and make it easier for us to adapt for if we had many fields. So say we had 10 arguments or so, like this task model got massive. We wouldn't want these arguments trailing off and like being a massive line, so we can use .quargs to simplify how we define everything. So we can say like self.description equals quargs.get description. So the .get notation, for those of you who aren't familiar with Python, it's just a way to access a field within any dictionary. So quargs is this dictionary that we're accessing, and we can default it to an empty string if there is no description provided. So the next thing we want to do is say done. We want to cast this to a bool just in case there is no the done field provided. So we could also have done this by just setting a default as false. But in case it's none, we can just show you that you can also default it as false by bool casting none will return false for you. So now that we've defined how to write some columns down and how to initialize our class, we also want to define like how we want to return this class object in when we print it or when we return in the response. Because as we saw earlier in the earlier assignments, we can only return things like JSON format with the basic types, so strings, ints, floats, booleans. So if we have a task object, we can't just ship a task object within a JSON. We need to convert it into these basic types again. So this is called serialization. So we're going to make a serialize method. And what we need to do is just return a dictionary where we can say description is going to be self.description, and done is going to be our done field. So that's all we're going to do for right now, but let's hop on over to app.py once you all are finished typing this up. And so when we go to app.py, we'll have all of the same routes that we had in the last demo. So just getting all the tasks, creating a task, updating, deleting, getting a singular. So we're just going to redo those in this ORM structure. So we'll also come back to db.py later, so in case you didn't write everything down. But moving on to app.py, the first thing we need to do is if you have the demo code on Piazza, all this stuff is all here for you, but you can just comment out and get rid of some of the old syntax that we're using before. So the things to notice is that we're importing our task class from our DB file. We're naming our DB file name, and then we're putting down a bunch of configuration things. So notice the SQLite flag, that's indicating to SQL Alchemy the type of database that we're using. Some other types you could use are like Postgres, but for us we'll be using SQLite so that it knows, and then you want to provide the file name that we defined before. And these are some other flags that you don't really need to worry about, but if you have them in your application, it'll work okay. So the next thing we need to do is just how in when we were doing raw SQL, we had to initialize all of our tables. That's kind of what we're trying to do right here. So we want to do what's called initializing the application, and db.createAll will create all of our tables for us. All right, so now getting into our first route, the /tasks, getting all tasks. What we had before, the db.getAllTasks, we want to replace with some new syntax. So the first thing we can do is get our tasks by just doing task query and then all. So the .query is something that's inherited from the task class by using the db.model provided in SQL Alchemy, and allows us to run easy queries. So in the case of all, it'll be just like a select all from task table. So now we can replace these tasks by, say, we want to serialize each task in our tasks array. So because we're using the .all query, this will return us a list of all the tasks. If there are no tasks in the database, it will just be an empty list, and then this evaluation will still be an empty list. So we're calling t.serialize, the method we just wrote, to convert our task objects into these basic types. And then we're turning this result into a JSON file for our request.
So we use Serialize. If you can imagine, what we used before is like when we had our DB file and then we selected everything from tasks, but then remember when we created the new task object where we set like ID equals row 0 and then whatever equals row 1. You can imagine that as serialization, as in we're taking this data from the database and we want to convert it into something else, like parsing it into a different format. That's called serializing, and that's why we have the serialize function in our task class.
Yeah. So looking at the next route, creating a task, before we were just defining a simple Python object here, and then the ID was setting to the insert table function. And what this was doing was the data, this would actually be where we're creating the task in our table, and it would return the last row ID, so the new ID with this task object, and then we would return all of this back into a JSON dumps. But instead, we can create our task by just instantiating it directly from our class. So we can say task is task, and we can indicate our field's description is going to be this description that we indicated and pulled from the post body, and our done field is going to be also pulled from the post body by using the same .get syntax we've used before. And hey, why not do it like this too?
So the difference between just directly accessing the field versus using the get method is that if it doesn't actually exist, and you try to get it by key, then it's going to throw an error. But using .get will handle any like non-existing values for you. And that's why we have the second argument there to provide a default value if it was none.
Yeah. So now that we have this task, we can just serialize it instead, and it will give us this dictionary-like form. So we can get rid of this, and we can just do task.serialize. So as you can see, our code's already getting a little bit cleaner, and we just by like defining an instance of a class and then serializing it at the end. But one thing we are missing right now in creating a task is we need to actually add this to the database. So just because we instantiate the class, task is just a local variable, but we need to commit this straight to our database. So we've imported, we need to import the database at the top, but now we can just do db has this field called session, and we can just add this task object to the session. So one thing it also handles for us, which is really nice, is we'll be using db.session.add to handle like all additions to the database, and so it can like infer the table based on the class type that's coming in. So that's really handy for us. And then after we add it to the database, we want to save these changes with committing, just like we did before using raw SQL. So one thing that's also key to understand about making ORMs and interacting with databases is the separation between adding something to a table and saving it with a commit statement. The reason we separate these two is to basically, there are two main reasons. One is to like save runtime. Imagine if every time you add to the database, it also automatically committed for you. But say we wanted to add like 100 items to the database at the same time. We would have to add something, save it, add something, save it, and it would add a lot more to our runtime versus adding everything at once and then only having to save once. So makes our SQL queries, makes us need less of them, and also makes the query time faster. It also allows us to better separate and minimize what's called like race conditions. So say you have two users or like two queries trying to operate on the table at once. SQL and like what your server has to determine which operation to execute first. So by spamming committing on the database, you just add more queries onto your tables, and it makes race conditions harder to evaluate for the database. So by separating these, we have less SQL queries overall, and it makes it easier for tables to keep up to date and add stuff. All right, the next thing we want to update is how we get a singular task. So before we were using this custom method get task by ID, but now we can use what SQL Alchemy gives us with the same task.query, but now we can do something called filter by. And filter by will function just like at the end of a where statement, so we can define the Boolean expressions we want to input. So for us, we want to filter by ID equals task ID. So what this will do is, this is the equivalent of saying a select all from task where ID equals task ID. So for us, we don't want just all of the tasks that can match its ID. Hopefully it's just one if everything goes accordingly, but this will return us a list, but we actually only want one singular task. So we can use the dot first to evaluate this just to a singular task. And then here, if we don't have the task, i.e. if it's none, and dot this will return none if there is no task in the table that has the ID we're looking for, then we'll give an error back, but otherwise we can just give back our task serialized. So let's see if we can actually pull these out in Postman and see if we get something going. So, not small. Oh. Okay. So we're just going to run our application here. And we can see everything's going okay. So now let's go to Postman and let's first look at all of our tasks. So as you can see, we're hitting our server just like we've been doing before with tasks. And right now we have nothing going on. We just have no data. So let's see if we can actually create a task how we wanted to before. So before a body, let's see, we want to define a JSON body. So before we just needed to define a description. So let's say do study for prelim, because it's prelim season. All right, so let's first test to see if we don't even need to provide the done field, and let's see if our optional handling is working properly. So if we send this request, we get that this works properly, and the done field defaulted to false for us, which is nice. So now if we go back to getting all of our tasks, we can see it is there correctly, which is wonderful. So let's also see on the console, we can actually see the SQL commands that our server had to run to implement all of this. So you can see it created the table task for us. This is like the pragma, if you remember from foreign keys, but it's also just printing some syntax here for us. But now here we can see one of our first queries, the select task ID and description. So these are naming its columns. So we're just selecting the columns from the task. So you can see when we made our first one, our first insertion, we can see insert into task, description, and done, and then the two values. And then these are the two values that were provided in the request. And then when this is our final query to select everything. So now we can continue on and implement the rest of these routes. Let's start with updating. So when updating, we're using this method, but we're going to do it manually now, or just a different way. So we're going to get our task first, the same way we did before. All right, so and then if this task does not exist, then return not found. But otherwise, we want to update it, and we can do so just by manually editing the field. So we can say task.description equals description, which we will also want to do .get. And actually, we're going to move these down below. And the reason we're doing this is we want to default the field for description to be actually the old task description if it's not provided in the post body. And we're doing this because we don't want to have to pass the entire object whenever we send a request and want to update it. We only need to provide the fields that we actually care about updating. So for now, we can do post body dot get, and this will default back to task dot done, and we have this bool. All right, so now we can just set task.description back to description and task.done equals to done. So and then we want to save these changes, so we can just do db session.commit. So as you can see, like the logic, it isn't really changing that much. We're still parsing the post body. We're still trying to grab our task with whatever means we have available to us. And we're still trying to parse our inputs from the body and then just update our task and then save the database at the end. So now moving on to how to delete a task, we will just still get our original task as before. If it doesn't exist, say it doesn't exist. And then otherwise, we can do this thing called db session.delete. And now we can delete our task, and of course we want to commit these changes after the fact. And I forgot to serialize right here. Cool. So we can check to see if these work. Let's try to update our tasks. Say we want to say that original task with ID. Our first task we want to say is done now, so we can say done and true. And let's see what happens. Cool. So now it says it updated properly, everything's all good. Now let's see if we can delete this task. We can say task 1. And cool, it's gone. It says it's gone. Let's make sure. Yeah, it's gone. Cool. All right, so another thing that we may want to do when having these tasks is having subtasks. And we can do that by defining another model. So let's go back to our db.py file and define a subtask class. So this will be the same db.model inheritance, and we also want to define a table name. So for us, this will just be subtask. This too will want we will want an ID, so we can just copy that. And we also want a description too, why not? Actually, we're going to copy all these fields. And then like here, we want to define how we want to initialize it. So we'll do the same, self-quarks. Oh, wow, this is crazy. Let's just copy all of this. Cool. One thing we're missing here from its subtask is we want this relationship to be one-to-many, so we still need to define a foreign key. And we'll do that by typing down task ID. And this is where we can do a column, but now our type is going to be an integer, but we're going to add one more flag to make it extra special, give it some special sauce, you know? We're going to give it a foreign key reference. And we're going to call it the reference to the task table and reference the ID field. That's what the .id stands for. And then we also want to make sure that this is non-nullable. So whenever we have a subtask, we want to create it under a parent task. So we're going to enforce that it has this task ID field has to exist, can't be none. And then now what we can also do is, let's define the ID, why not? And we want to, say we want to like serialize this subtask within our main tasks. So saying like the last assignment you wanted to serialize your transactions within getting a user, we can do that easily by just adding some more lines to our serialize function in the task class. And we can just say subtasks equal, oh, I'm actually going to miss something here. I want to need to define the subtasks back in the task model. So just because we define it in one place, SQL Alchemy, to make sure that the foreign key references are working properly, requires you to define a field in the parent table as well. So tasks, we will define its subtasks, and this is where we can define a DB relationship. So a DB relationship will just enforce the same restrictions as the foreign key and successfully create that linkage. And we want to reference the class name we're referring to, so subtask. And this last flag is called cascade. This cascading is a protocol in one-to-many relationships that allows you to delete many things at a time. So what I mean by this is, say we have a task with many tasks beneath it. If we delete the parent task, we should want to delete all of the subtasks that it had along with it. And this helps us enforce that the task ID is non-null as well. Because if we delete a parent task without its subtasks, then this will refer to nothing, and then we break this constraint. So by cascade deleting, it just says, if I delete this instance of a task, delete all of its children. So now back to defining the serialization, we can just do s.serialize for s in self.subtasks. So, but when we reference self.subtasks, it's just referencing like a regular list, which allows us to do this clean for loop syntax. Okay, so the next thing that we want to do is go back and define some new routes to be able to create subtasks and see if they actually come up when we query on our regular tasks. So actually we can try to, the DB did refresh, so we can go back to get all tasks and, and we should remember to initialize this as well. All right, cool. Oh, didn't fix it. Okay, all good. So we're gonna go back to app.py and let's add a route for adding a subtask. So like before, we're just going to define our route the same way we were doing before. And now we can choose to add a subtasks. And we want this method to be post because we're sending data with the post body to create a new item. And we can define create subtask. Just like before, we want to get our task object to see if it exists first off. And then otherwise, we'll proceed as normally with parsing the post body with the json.loads and creating our subtask object, so instantiating the class. So we'll say subtask is subtask, which we need to define in the imports so it doesn't get mad at us. And like before, we need to provide a description, so we can just say post body dot get description, default to an empty string. Done is going to be post body dot get done, and we can just default this to false with this way too. And the final thing we need to do is indicate the task ID, which is just going to be the task ID taken as an argument from the route. So now, like before, when we were creating tasks, we want to add this subtask to the database. So we can just do subtask. And we also want to update the task that we were talking about initially by doing subtasks.append, and we want to add the subtask to the list. So a way you can think about why we need to do both of these is the db session.add will actually add this subtask to our subtask table, while the .append will just make sure that we're enforcing that the task reference is working properly and we're actually creating that relationship. And then of course we want to commit these changes. And when we're all good, we can return everything is chilling. And for us, we'll want to return this serialized subtask. So now if we want to try creating our subtask, let's go here talking about task 1. And let's do, so the task, this parent task is talking about studying for a prelim. We can do review lecture notes. And done, it's going to be false. So if we send this request, task not found. Let's see, let's go back to getting all of our tasks. Oh, we have no tasks. Yeah, we deleted it before. So we can go back here and remake this. Cool. Cool, and now you can see that we successfully created this. And now if we get back to subtasks, you see from the last query, the subtasks field was an empty string, an empty list. But now if we refresh the request, we have the subtask serialized within using the syntax we were using before. So super straightforward, simple approach using ORMs to do these types of things. I guess any questions so far about using the SQL Alchemy ORM, defining our tables, and creating this relationship? Cool.
So another reason why we use serialize, or why we define it, is, so remember that within your subtask, you're defining like a task ID, right? You have like that foreign key that goes to the task. But you can see that when we're returning the JSON, we don't really care about what that value is, because you know that it's going to be like, the task ID is going to be the ID of the task you're actually looking at. It's kind of redundant information. So because you defined in your serialize that you're not returning that task ID, you're only returning all the other information, you can basically have more control over what you're sending back.
Cool, so this is like a demonstration of how to do a one-to-many relationship between subtasks and tasks, but we also want to show you how to do many-to-many relationships. So say for like a certain task, like object, like I want to assign it some high-level category ideas. So for me, I use Todoist for like keeping track of my stuff, and I have like sections for like this is homework, or like this is like working out, or like health-related things. So we want to create something like that in our to-do table, to-do database. So we'll define a model just like before. Table name, let's call this category. We want to make an ID. And let's also snag a description, like a text field. And let's also give it a little color coding action because colors are fun. And this will just still be a string for our implementation right now. So we also want to define how we initialize it. So self and quargs. So we're going to do quargs get. Ooh. And we're not going to provide a default for color because we'll just let it be none, and that'll be okay for right now. So then last thing we want to do is define how we want to serialize this. So it's the same approach. And for right now, we're also going to serialize the ID too, so we can see if our many-to-many relationship is working properly. All right, so just because we created this table, we actually haven't established a relationship yet. And so I guess, Ed, does anyone recall when defining a many-to-many relationship, how we actually implement this with SQL in terms of tables? Yes.
You have like another table that has the IDs from one table and the ID of another table.
Yeah, exactly. Yeah, so we're going to create what's called a join table, or also known as an association table, to link these together. We actually don't have to define this table as a typical class. We don't really want to because we don't want to confuse it for like a model we actually care to manipulate and store real data in, but we just want to use it for the purposes of creating this join nature between the two models. So we're going to do that at the top, and we can just define like a variable association table, and we can use actually a db.table to manually create this table for us. We're going to call it association, and we have to pass in this db.model metadata. to work properly. And then now we can create our columns, just like before. So on one column, we're going to have the first ID we want to reference, task ID. This is naming the actual column in this table. And then we want to define its type, so it's going to be an integer. And it's also going to be a foreign key, because it's going to reference a field in another table, that table being task and the field being ID. And we're going to define a second column here for our category ID, which is also going to be an integer. Cool. So now that we have created this join table to allow us to create this many-to-many relationship, we now actually have to create these references in both the task class and the category class. So on the task side, we can define this field called categories, just like how we had the reverse relationship for subtasks. And this too will be a relationship. It's going to be referring to the category class. And now we have to pass a field called secondary. And this is just indicating the exact table we'll be using for setting up this relationship. So we're passing this variable that is a table here. And then we also need to pass in this field back populates. And so what back populates will do, it's kind of like giving us a name to access the task object from the perspective of the category. So it's like back populates is like you're going backwards. So if say we had a category object and I wanted to get its task, I could do that by doing that category dot tasks. And that would return me back a list of all the tasks related to that category. So similarly, we want to do the same thing in the category class. So going down back to the bottom, we'll define, so now we want this to be, there we go. We want this to be tasks. It's going to reference the class task. It's going to be using the same association table, but in this back populates we can use as categories. So another thing with the back populates is the name we're providing here has to match the name we define in the task class. So if you recall just above, we defined the back populates previously to be tasks. These names have to be equal and line up for SQL Alchemy to successfully create this many-to-many table for us in this relationship. Cool, so now that we've created this relationship in our table, we can try messing around and adding some routes to actually deal with these categories. But actually before that, we want to serialize the categories of a task back at the serialize. So we can say categories, and we're going to follow a similar style of serializing each one with this nice looping syntax.
Yeah, if you guys are curious, it's a feature in Python called list. What is it? Wait,
Spreading?
No, it's not called spreading.
Comprehension.
Comprehension. There we go. Yeah, it's really nice. There are a lot of. You can also do it with like dictionaries and sets with the syntax.
Yeah. All right, so let's start adding some routes for us to mess around with. So let's start with. Let's use a similar structure for the subtasks. Ooh. But now we want to do, say, category. And we also want to make this method a post because we're trying to, we're going to pass some stuff in the body with this request. So we can say we're going to assign a category to our task with task ID. And let's just do a little bit of this. All right, so we want to get the task like before. If it's not there, we want to immediately return an error saying that task does not exist. Let's parse our post body, but instead let's create a category. And we're going to use category. Oh, I'm forgetting to import stuff. Don't forget to import at the top. All right, so now we can use the same description, but now we have done. That will be replaced by color. Actually, we'll just do the. And we don't need to define this task ID. So one thing to, we need to append this category, almost there. So one thing that's not great about this code as it stands right now is each time we try to assign a category, we're going to create a new instance and add it to the database, but this kind of repeats like the purpose of doing the many-to-many relationship and like conserving the space that we use. So say if I were to like say make a homework, like a category called like homework and give it a color red, and I did this request twice, I would have two instances in the category table that had both the homework and red combination, and that kind of defeats the purpose of using the relationship. So we first actually want to find if this category even exists. So we're going to do that with query, how we're doing before, and we're going to filter by again, and let's just see if we find one with the description that we're looking for. And we want to get the first one that we can find. And then if this category does not exist, if we don't have one, then we can create a new one. And then we can serialize the category if we want. And make sure to add the tasks, this category to its categories field. Cool, and because we previously added categories serialized within the task, we can check that this works without adding any other routes. So let's go back to Postman and try to assign a category. So let's go local. Our task is 1, and we'll do category. Cool. And our body, we can do like a homework category, and then let's give it a color of red. So now when we send this request, because the task doesn't, this category does not already exist, because this is our first one, it should create a new one for us and assign it to the task object indicated with ID 1. And hopefully,
A post.
Oh, thank you. This needs to be a post request. Cool. Cool, and now if we go back to get our our task, we now see that we have this categories field and it's a list, and we have this one category flag called homework. So just to make sure that the previous logic we were trying to do is working properly, let's just try spamming this again. And as you can see, by triggering the request again, it did not create a new category for us, and it did not assign like a duplicate of this category to us, and everything's conserved as indicated by having one category here. So now just to make sure this many-to-many relationship is working properly, let's create another category, say sleep, health. It's going to be blue. Cool. ID 2, that's good. And let's create workout. And let's assign health to working out as well. Cool. So now we have our second task here, workout. No subtasks, but you can see it has this category of health with blue as its color. Alrighty, well, this kind of concludes what we got to show you for the demo. I'd like to also highlight this, the SQL query. Again, as you can see, it's going through our association table with like this join query that we showed like last lecture. So it's just trying to put in like this nice where statement where we're trying to find the task that matches with our task ID from the association table, and the category ID matches the category ID also from this association table. Yeah, so that's kind of what we got to show you, but I want to go over a little bit of our assignment this coming week. So we're going to be having you do kind of like a pseudo CMS. So you'll have like a handful of models to work with, like students, so like users, courses, and assignments. But yeah, let's collapse these. We don't have too many routes for you, but the big thing is understanding the relationships going on with stuff. So we hope you can use what you've learned so far to understand the relationship between assignments and courses, and the relationship between users and courses. The one thing to know about creating a course, creating a user, is that, users, we have two different types of users involved in a course. So we either have students or instructors teaching it. So this will actually be like the same models. Some people in the past with this assignment have created different models or different associations between users and courses, but you only need one association, and you can just flag in this user model with the type of user it is, and it will work nicely for you. So that's like the big thing we wanted to show you with this assignment for right now. Do you have anything else to add?
I think something else to look out for is, so you see here that before we kind of represented our placeholder variables with these brackets. So it was like course or like task or whatever. But now you see that we put serialize course. So the reason why we do that is because we don't want, so say like you have some sort of model in your database and it has a lot of different fields, but we say serialize because, again, we don't want you to return all the fields. So a reason why you might not want to do that is, so think about a course. A course here is going to have instructors, but an instructor is also going to be enrolled in courses. So if you try to print out all the courses that an instructor will have, then it's going to inevitably print out this course, which will have the instructor, which will have the course. Basically, you get an infinite loop of information. So when we say like serialized user, we want you to give the user's information. So we have right here, when you create a user, you have like a name and net ID and like an ID. We want you to return that, but we don't want you to return the courses field. We want you to omit that. Anything that might potentially cause this like infinite recursion of like information, we don't want you to return that in your like JSON response. This is very important. We had a lot of Piazza posts about it last time saying that their like computer crashed or whatever when they did this. Yeah. So yeah, if you have any questions, feel free to come up after class. Otherwise, dismiss.